Hello and welcome to the progress update from Team 20, the tart cockroach cohort. We are working on the Botanexia greenhouse environment monitoring and alert system. Our focus is on the novice or urban gardener, a massive user group facing a critical issue in constrained spaces like apartments and balconies. The core problem is inconsistent environmental conditions. Unstable light, temperature, humidity, and soil moisture levels cause low yields and high plant mortality. We were tasked with designing an affordable, small-scale monitoring system using our TI-Kit microcontroller and a Grove-compatible sensor. Our goal, a reliable alert when conditions fail. I am Ethan and my teammates are Sanjith, JP, and Steven.
Before we designed anything, we investigated existing solutions to understand their limitations. We quickly realized that most large-scale systems are too complex. For example, a greenhouse intelligent monitoring device is mechanically complex and costly. It lacked sensors to monitor critical conditions like soil moisture, despite its large size. This showed us that complexity does not equal capability. Other commercial IoT-based farm monitors rely on unreliable wireless protocols like Zigbee, which struggled with interference in crowded urban environments. Additionally, complex and costly designs would not be appropriate for the novice urban gardener. Therefore, our solution had to be simple, robust, and free from external connectivity dependencies.
Our brainstorming led to several concepts centered around tracking soil moisture. Three stood out for prototyping. First was Casper, a rugged protective structural dome focused on maximizing durability and good ventilation. It featured vents at the top and bottom of the structure, a water collection system, and stakes to help anchor it into the soil. Second was the Honeycomb, which emphasized localized, detailed data visualization for the user. It used hexagonal cells that would sit inside the soil, monitor moisture levels, and display it for the user in a separate device. The cells would be controlled by a central node and would activate the irrigation system when necessary. Third, and ultimately our final choice, was the living lung, an autonomous, biologically inspired structure focused on low-power passive control. The affordability constraint was $50. Casper was too costly because it was complicated. Honeycomb's detailed display also added too many components. The living lung, with its simplified passive structure and low component count, was the most cost-effective. It also scored highest on energy efficiency due to having few electrical components that needed to be powered.
The data supported the choice. We confirmed its functionality through our weighted decision matrix. Utilizing our weighted decision matrix, we weighed 4 different categories with their own subcategories: cost, ease of use, energy efficiency, and durability. Across all of our tests, the living lung proved to be our design with the most beneficial structure and usable design. Its simplicity and low component count proved to be its greatest strength, meeting the high standards for reliability and cost. Our final design is the living lung, which integrates the best features from the alternatives. We kept the durable outer structure from Casper, but we eliminated power-hungry fans for circulation. We hope to incorporate an aerated biogel that expands and shrinks based on the general humidity in the greenhouse, thus giving us the name Living Lung, an essentially electricity-free system of moisture adaptation. The cactus rib-inspired outer shell and ribbed inner shell allows the addition of the biogel without affecting the growth of any crops. The final major iteration addressed a key limitation. The original design of Living Lung was too autonomous. Users want more control. We added localized visual soil moisture mapping using multiple in-ground sensors, adopting the visual clarity of the honeycomb concept.
Our final solution has limitations, primarily the need for a protective, durable enclosure to withstand high-speed winds that could damage or dislodge the system from the balcony. However, fixing this through added bulk and weight trades off through absolute portability. For future work, we'll focus on integrating a more sophisticated self-calibration algorithm into the MSP430 to maintain sensor accuracy across different soil types over time. In conclusion, the living lung is a validated, affordable, energy-efficient, and innovative solution for urban modern gardening, supported by engineering principles and data. Thank you. We here at Team 20 are excited to share our next steps soon. And here are our references.